Gloriana Monko. I'm an author and I'm a PhD candidate. So today I'm presenting our paper, which goes by the title, Optimized DBSCAN Parameter Selection with Stratified Sampling for Epsilon Estimation and Gridsearch for minimum samples. So I will go quickly to the presentation overview, which will take you through the background information, the methodology, results section, discussion, and lastly, I will finish with the conclusion. So our research or our paper focuses on improving clustering algorithm, which is DBSCAN, density-based spatial clustering with application and noise. And we understand that clustering algorithms are very crucial in uncovering hidden patterns and structure within dataset. So there are several different clustering algorithms, and one of it is DBSCAN, which is a highly regarded and supervised machine learning algorithm, among other density-based clustering algorithm. So DBSCAN actually differentiates itself with other clustering algorithm for its effectiveness in identifying clusters in dataset or in dataset with diverse shapes, sizes, and which are not falling into spherical groups. So it makes it different from other partition-based clustering like k-means and hierarchical means and other clustering algorithms. So that is one of its effectiveness, and it has been the strength. But another strength of DBSCAN is being able to classify the clusters and the noises, to separate the clusters and the noises. So that is one of the salient feature in DBSCAN as well. And the whole concept of DBSCAN comes with how it can identify, but it can identify the clusters, focusing on the density by using the density concept for those data points which resides in high density region or in most populated density region. They are being clustered as they are being categorized as clusters, and the ones which are residing on the low density region, they are being clustered as outliers. Something that most of the clustering algorithm, they cannot differentiate these aspects. So this is one of the salient feature that DBSCAN carries. And how does the DBSCAN identifies or differentiate those points? It looks at the core points where it is selected randomly from the data points within the data, and then it looks at the nearby data points, which are actually measured using the EPS value, which is the radius from one point, from the core point to the nearest neighbor point. And from there is another factor or another aspect which actually guides to identify or to make sure that, to say that this is a complete cluster. So another aspect to consider is usually a minimum sample, which actually describes the minimum number of data points which are supposed to be considered to form as a cluster. So if the minimum point is not reached, that cannot qualify to form a cluster. So DBSCAN checks on these two parameters, which are really guiding it to identify that whether this is a cluster or this is not a cluster. So looking at the nearby neighbors, for instance, here we have the minimum sample of 6, and then, for instance, we select this one as a core point, and then the rest or the nearby the data points, if they reach the minimum number of samples, then this can qualify to be considered as a cluster. As for the rest of the data points which are not qualifying for the two major conditions, they do not fall under that category, and they are being considered as outliers. So that's how DBSCAN works. But the problem here that DBSCAN, regardless of its advantage and the strength that it has over other algorithms, it still suffers from the challenge of these parameter selection because they are not, they are manually input, and you cannot just, so you need to really be carefully when deciding or when selecting an appropriate value for the two parameters, which are epsilon and the minimum sample. So selecting an appropriate EPS value is a challenging factor in the DBSCAN, because the larger the value might cause the clusters to merge, while the smaller the value, it can also tend to regard or to make the data points, many of the data points, to be labeled as noise points. Likewise, the minimum point is crucial, equally just like a epsilon value. So having, when you set the minimum value for minimum point to be greater or too large, it can also cause too many points to be identified as noise. And when it is too small, it can also lose the information of, or the clusters may lose the meaning or the information. And so these, the DBSCAN, really it is influenced, or the performance of DBSCAN is really influenced by these two major parameters, which is epsilon and the minimum sample. And if we are going to make a poor decision or make a poor choice of having these parameters, we can, it can lead to inaccurate cluster overfitting and also high misclassification of these clusters. So those are the problems that we are trying to solve in our research, and our methodology actually focus on determining the two major parameters which are guiding the DBSCAN into clustering. So the first cluster, the first parameter that we spoke about, which is the epsilon, actually we used the stratified sampling to determine the epsilon by segmenting the data into homogeneous group by creating strata or subgroups. And the reason why we had to consider the stratified sampling concept is because we understand that these data points are located in different regions. There are some which are they are very close to the core point, and the others are very distant from the core points. So when they are selected, or when you select a data point randomly, so you might end up selecting the one which is of a maximum distance or very small distance. So what we wanted to have is to be able to ensure that we choose a subset accurately reflecting the diversity of categories by having, a representation in all data points, so that, across the data set, so that we have a more distance calculation which can capture all the points equally. And this was to help us to mitigate the risk of selecting points only which are residing on the densely populated region. So we wanted to reach even the less populated points, and so that we can have a more reliable distance calculation between the target points. And another aspect that we used, or the approach that we used for the second parameter, was a Gridsearch approach, which was to determine the minimum point or minimum samples. And this one is tied to the initially calculated EPS radius. And so once we calculate the radius is when we can determine the minimum point, because we keep the radius constant, or we keep the minimum, the EPS radius constant, and then we loop in a certain range of values to find for the best minimum sample that can actually return the best clustering results. So this is a workflow which actually summarizes what I've just said in the previous slides. And we had utilized two types of data set, the artificial data set and the real world data set. And The artificial data set were of only 2-dimensional and they were in numerical format, so they did not require much of conversion, unlike the real world data set, which actually required to have data, to do the dimensionality reduction because they were of high dimensional data set. And so we had a data pre-processing, and then after that, the process that follows was to set the number of neighbors, and this number of neighbors actually depends on how on the number of the data set. And yeah, so it hugely depended on the number of data sets that was used on a particular on a particular data set. So the data size actually guided us to selecting the number of neighbors. And then later we calculated the average distance using the Euclidean distance. And unlike the conventional DB-SCAN, it was just using the cave distance instead of using the average distance. So, and as for our case, we use the average distance so that we can also capture the central tenders, so that we can have more representation, or to be able to have a more representation of the data points across the neighbors. And later, we performed stratified sampling, which carries the name of the methodology used for determining the EPS value. And then we performed the polynomial fitting to estimate the EPS value. But likewise, after we have calculated the EPS value, we were supposed to set a minimum range, or a range to calculate the minimum point. So the minimum point was calculated by keeping the EPS value constant, and then we perform grid search on a certain range, and we actually considered the three. We considered the initial points to be 3 instead of 1, because 1 you just end up having 1 cluster, and 2 is not good enough. So you can range from 3 to n number according to how it is going to end. And then once you get the value of minimum points, you select the best fitting by using the slot score. And then we pass the 2 parameters in DB-SCAN clustering, and then we get the clustering results. But how do we attain the best result? For us, we use the slot score to go the best, to see whether we have gotten the best result for clustering or not. So if we are not really comfortable, or we are not satisfied with the result that has been attained, we look at the slot score. If it is less than 1, we loop, and we can come back and set adjust the number of neighbors to see if we can get the best results. And then the loops goes through the same stage, the same process, or the same steps to attaining the best slot score for the clustering. So this is the mathematical theory for EPS estimation behind what we did, how we employed the average distance from point X to its K neighbor to determine the value, as I mentioned. And the reason why it was to have a broader view of its local structure, and also to be able to provide a more holistic perspective on the data relationship. But again, the use of class interval was also another approach that we used to create the so-called subgroups, or the stratas. And this one was attained by defining the number of, or initializing the number of bins. For instance, we want to have 4 groups, or 3 subgroups. So we initialize the number of bins, and then by having a range, by having the distances calculated, we input, and then we get the subgroups of those distances in a certain number of bins that we actually initialized. And after that, we apply the stratified sampling. So we use the sampling rate of you can use any sampling rate, for instance, if it is 50, 60, or you want to return 80% of your data. So from each strata. So for our case, we used 80% to determine this one, but it is something that a user can actually define according to how he or she sees it fits. So, and if there is a sampling imbalances arise across the bins, we handled this by using the upsampling technique. The reason why we wanted to end up, the reason why we use the upsampling technique is because we wanted to end up with equal representation of the data point across the bins. So for some of the data which were of an even data set, they ended up having an equal number of data points. So we used the upsampling techniques, which actually eventually optimized our algorithm performance by having an equal representation of data points. And this is an algorithm of how the Epsilon estimate, Epsilon was attained from how we select the data points and how we calculate the distance, the average distance, and how we applied the stratified sampling, and we constructed the k-nearest distance graph, which is k-distance graph, and locate the Epsilon value. And after that, we came to the Gridsearch, where the Gridsearch was also, as I mentioned, that we used a range from 3 to n point. So you can put any number of steps that you want to make, if it is 1 or 2, but I would recommend for 1 so that you can have a better values. So this is how we did, but the distance or the Epsilon value that is set constant is the one that which has been acquired. So by keeping it constant, we range through a certain range of a range that we put, or we initialize, and then we use the slot score. The one that returns the best result or the highest slot score is the one that we use to attain the best result for our clustering algorithm. So this is an example. This is just an example of how it looks like attaining the minimum sample. So you can see the average, the minimum sample of different slot score. So the one with the highest slot score is the one that is going to be used to feed to the DBSCAN clustering algorithm, and later we get the results. So in our experiments, we use dataset, as I mentioned, that we use dataset of different type, the artificial and the real-world dataset, and they varied in size, dimension, and also the structures. So the objective of this experiment was to evaluate the resilience and the flexibility of our method, if it can fit in different type of datasets and dataset of different dimensions. So these were the results. As you can see, for instance, this is our algorithm, and this is the one that we are, the conventional DBSCAN. And the true data set has the 19 clusters, or the 19 true labels, and ours ended up returning the same number of clusters, unlike the DBSCAN, which returned 35 clusters. And the slot score, as you can see, they differ. And another one, this is another data set. As you can see, the DBSCAN, the conventional DBSCAN, was not able to do the clustering well. It ended up having 1 cluster, but ours, it ended up having 4 clusters, which were so much aligning to the true labels of the data set itself. And another example is this one for the real-world data set. And this one actually returned these results. As you can see here, the normal DBSCAN the traditional DBSCAN was not able to do a clustering well. and ours was able to perform this way and return the 4 clusters. And this is another example of the real-world data set, which you can see the differences, and you can see the performance of the two algorithms, how they performed. And that is just a summarization. But we didn't just end up there. We thought that it was important to not only focus on the slot score, but rather to validate our model or to validate our method using other metrics or performance metrics, including NMI, homogeneity score, adjusted rand index, completeness, and these were the metrics which we used to determine whether the model or the method that we came up with stands out compared to the traditional DBSCAN. So from this table, it may be a little bit difficult for, to show one-on-one, but this has been summarized in these graphs. As for the slot score, as you can see, the slot score was used, or the slot technique was used to check the likeness and the differences or the closeness of these of clusters. So when you look at the graphs, how it suggests, you can see how the SS-DBSCAN outperformed the traditional DBSCAN. Only one data set, which is IRIS, both clusters performed equally, but the rest of the results, our algorithm performed better compared to the traditional one. And coming to the normalized mutual information, which is NMI, we also use this to see how the resemblance between the two clusters or patterns can, compared to the baseline truth labels, they can. So these were the results. Looking at it, you can see some of the data set did not perform well at all. They were very, the performance was very minimal in the traditional DBSCAN compared to ours. So likewise here, the SS-DBSCAN outperformed the traditional DBSCAN. Coming to another metric which was used was completeness metric. And this was used to check whether the data points that, the data points which are associated with a specific class are also are consolidated within a single class. So this is how the results actually showed. And again, here, the SS-DBSCAN really outperformed the DBSCAN in its performance. And as for the adjusted rand index, this was looking at the distinction between the partitions or between the clusters. So how similar and how different the two groups or the data groups are. So this is how the results looked like. And yeah, so that explains about the experimental result that we made and the validation of our model or our method. And in our discussion, we actually determined that EPS estimation offers an edge over existing other methods. And it also accounts for the complexity of the data set structure, the density variation, allowing for a more adaptive region-specific determination of the EPS parameter, but also it provides an adaptability which is really flexible, and because we have these two parameters which can be fine-tuned accordingly so that you can get the best results, and which number of neighbors and the number of bins. So as a user can always change the number of neighbors or adjust or fine tune by using these two parameters. If you set a number of bins, maybe 3, and then later you set 4, you can see the differences in your results, how they can result into better or worse results. So you can change accordingly. And as for the grid search, it also suggests that our method has provided improved clustering results, not only in our case or in our improved SS-DBSCAN with the new calculation method of EPS, but even with the traditional DBSCAN or the conventional DBSCAN, when we tested, the results were much better using the values acquired from Gridsearch approach compared to the traditional norms of setting the number of minimum using either the number of dimensional times times 2. So the notable strength of our suggested method actually also lies in adaptability and its resilience to the diverse data set it can provide. But also another thing is a significance in reduction of its computational overhead, because with stratified sampling approach, we do not use the entire data set. We target only the segment, which can actually help in improving the performance or in reducing the computational costs. So that's how the two methods or the two approaches that we used in this particular paper deliver the best result for the clustering algorithm. So by integrating the K-neighbor approach, we achieved an enhanced accuracy in EPS parameter estimation, as also our method outperformed the traditional techniques and underscore the importance of tailored approach to handle varying scales, dimension, and densities. And furthermore, our grid search technique for minimum point estimation challenged the norms, highlighting the necessity for flexibility, especially in those high dimensional data sets. So our method actually indicates a promising path for clustering algorithm. And that marks the end of my presentation. Thank you so much.